Hi everyone, my name is Anshumali Kurmi and welcome to SIT221 tutorials. In this video, we are going to discuss SVO trees and understand the key concepts and how to create one. So before diving into AVL trees, let's revisit binary trees. Before we start with binary trees, we have to mention binary search trees as well. So starting with binary trees allow for at most two children in each node, but they lack a specific order for data insertion. Now the problem arises when there is no order during data insertion, and if nodes are randomly placed, searching, inserting, and deleting operations becomes challenging. The essence of data structures is to organize data efficiently for easy retrieval and manipulation. And to address this issue, we introduce binary search trees, which impose an order. The rule is to place smaller elements on the left side of the node or root and larger elements on the right. This ensures a balanced tree, which is crucial for efficient operations. However, binary search trees have their own problems, especially in the worst case scenario. If elements are inserted in a sorted or nearly sorted order, the tree may become skewed, leading to degraded performance. I'll show that in a bit. And to give you a better understanding of binary search trees, binary trees, and AVL trees and the relation between them, you can take a look at this graph. So all AVL trees are binary trees, and all AVL trees are binary search trees as well. But not all AVL trees, or not all binary trees, are binary search trees, and similarly, not all binary trees are AVL trees as well. So this was where AVL trees come in. So to overcome the limitations of the binary search tree and the binary tree, we introduced the concept of AVL trees, named after three Russian scientists who developed them. AVL trees are a type of balanced binary search tree that maintains a proper organization to ensure logarithmic height, resulting in efficient search, insertion, and deletion operations. Now let's discuss how to determine the balance factor of a node in AVL trees. The balance factor is calculated as the height of the left subtree minus the height of the right subtree. This value should be in the range of -1, 0, or 1 to maintain balance. If it deviates from these balances, the tree is considered unbalanced and we need to perform rotations to restore balance. Understanding the balance factor is crucial for identifying whether a given binary search tree is an AVL tree or not. In AVL trees, the height is limited to log n, ensuring efficient operations. And in this, you can see that this is a balanced search tree because if we calculate the balance factors for all the nodes, we can see that it's going to be one of these numbers. So the balance factor of this node here is going to be 0 because it doesn't have anything on here. Now it doesn't have anything here. So the balance factor is going to be the same, 0. It's going to be 0 for all of these nodes because -1 plus 1 is still going to be 0. But now, uh, if we were to remove this node, for example, then this is still going to be balanced as the balance factors are still going to be in the range. So this is going to be 0, so going to be 0, but this one is going to be -1 now. So, and then this one, so all of these were supposed to be 0, but here, -1, -2, -1, -2. Okay, never mind. So this is still 0, but now after we remove another one of these, so if we remove another one of these, now it becomes unbalanced. So the balance factor of this is now 0, but the balance factor of this is now -1. But since it's not at log height, this is still unbalanced. I'll talk about how to deal with that in a bit. But also the thing about skewing is this one. This is the example of how a skewed one would look. So this is what would happen if a binary search tree, so not an AVL tree, would work if it was basically sorted. So it's just going to keep going in one direction instead of turning into an actual tree. Now, to create an AVL tree, rotations are going to be a very key factor of that. So let's start with focusing on the rotations first. So when you start off with creating a AVL tree, we focus on keeping it to the left or the right based on the value. So if it's less than the number, we insert it to the left, and if it's greater than the number, we insert it to the right all the way until log n. Now after each insertion, we have to do a search, or we have to check if the tree is still balanced or if there needs to be more rotations. So there's 4 cases of rotations: the left case, left case, right case, and right case. For case 1, consider a scenario where the data is inserted in a way that leads to a left transformation. So imagine that the data is inserted like 10, 9, 8. In this case, a single clockwise rotation is performed to restore the balance. So to help you visualize it better, just think of this going to the right over here. So going down here, and then the connection with the T3 is going to be made with Z instead. And then the T4 is also going to be connected with Z, which it was anyways. So just the right rotation would solve it and turn it into a balanced tree. So even if you calculate the balance factor of this in this situation, and then if you calculate it, it's going to be not 0, -1, or 1. So -2, 3. So -3 plus 1 is -2, which is not balanced. Now, similarly for right rotation, it's solved using a left rotation. So similarly, take the Z and then rotate it to the left like this, and then connect it with Y, and then connect the Y's child to the new one, and then this one stays the same. And then now going to a more complex version of the rotations. So these are just combinations. So it's just going to be left after another rotation. So left will have something like goes to the left and then goes to the right again. So that's why it's called the left one. Similarly, why this is called the left because it's going left and then again left and then right, again right. So I think you guys got the point. So we start off by doing a left rotation on this side. So it's easier to imagine this as a swap rather than a rotation. So this one goes here, and this one goes there. And then for the children, we have to organize them in a way such that it's like reinserted with the AVL tree's properties in mind. So we still have to maintain the height, order, and then the balance factors as well. So considering that, and then the values, so it has to be less than this number, greater than that number. So we still have to take those into consideration. And after that, we'll be left with something like this, which is similar to the left case. So actually, it's the same as this left case. And then we just use the same principles in the left case to solve this. So this takes 2 steps to actually make it into a proper rotation. And finally, for the right-left case, the right-left case is also similar to the left-right case and to the right-right case. So instead of doing a left rotation first, we do a right rotation, or if it's easier to imagine, we do a right swap. So we swap these two, and then it turns into a right-right case. And after that, we solve it the same way we solve the right-right case, which is through a left rotation. So yeah, just imagine this going down, and then yeah, the children will have to be based on the properties. So it has to be less than this number if it goes to the left. If the number is greater than this number, then it goes to the right. So you just have to be careful of that as well. And that is all for this tutorial. Thank you for watching.